In this video something about radio coils. Of course this is a whole sea to drink, so I can only show a few things about radio coils. Here you see a few coils that I got with my dip meter from Monaco. Hope it's visible. With a dip meter you can stick the coil, this coil for instance, into the meter and then make it resonate. And here on the scale you can read on which frequency it resonates. I only want to show in this video how these coils look like. This coil for instance is a 173 microhenry coil. And these are the dimensions to give some idea about how such a coil looks like. It was made with very thin wire. I think it's more thin than ape hair. Very thin, many turns, and you can also read here on the coil for which frequency it's usable. And that means that when you want to make a coil for a lower frequency than say 1.5 megahertz, you need more turns than I show here. So you need quite a lot of turns. And here you see, for instance, a homemade coil on a toilet roll, covered in glue for a rigid PVC, and also a lot of turns. But especially when you want to go to long wave frequencies, you need a lot of turns. And there are also some issues on low frequencies that have to do with the very big inductance that you need on such a low frequency. For instance, on long wave frequencies you need 200 microhenry or perhaps 300 microhenry. And then there are some problems that can occur. I want to show first how such a coil for long wave frequencies looks like. It looks a little bit as if it is braided. Here are three examples. They must be sticked on a ferrite rod, and then they go to their very high inductance. So not only the way the coil was made, was wounded, but also that ferrite rod adds very much to the low inductance on low frequencies. And the problem with these coils on low frequencies is this: the own inductance, the internal inductance, and much more important, the internal capacitance. I say inductance, I mean capacitance. When you have a one layer coil here are all the windings, and you make a second layer on that coil, again here windings, or a third or a fourth layer, all these windings couple together capacitive, in a capacitive way. So that means that here you can see that again the windings and these windings couple capacitive, and all the windings couple capacitive. That means that every coil has a self-capacitance. And to prevent that, these coils are made, say, somewhat sloppy, as if they are braided. And I can assure you that you can have a better results on low frequencies, very low frequencies, when you wind such a coil sloppy. So this way, and then back in this way, and again such, the third layer and the fourth layer. And you can see in that case that there is less capacitance, internal capacitance, between the windings. And that's the reason also why these coils look as if they are made on a braiding machine, if such a machine exists. Back to the coils. 173 microhenry this coil, 37 microhenry, and you can see that this coil was made with a wire that's not so extremely thin, and it's all for that purpose, to get to that frequency band. And in this case the frequency band is 3.3 to 8.0 megahertz. Again, the next coil, 8.8 microhenry, made with, again, thicker wire. I hope it's visible, that my magnifying glass works good. The diameter is approximately 1 centimeter or 9 millimeters. I cannot decide that at this moment exactly. And here a coil from 1.2 microhenry, and then we are surely in the shortwave band, and this coil goes from 1.8 up to 45 megahertz. And of course all these coils need a certain parallel capacitor to get to these frequencies. So here we have the classical tank circuit. I never succeeded in going to higher frequencies than 18 megahertz, but of course this coil is related to the dip meter. It was made for that purpose. So I'm sure the engineers did a good job, and this will be good. I can trust it. Here again, two coils. When we go to the very high frequencies, coils, radio coils, can look very different. Here for instance you see coils for a high frequency, and in fact this looks a little bit like a hairpin, and really when we go to 400 megahertz or 500 megahertz, coils look like hairpins. Okay, well, that was all there was to tell about these coils. Coils are always made for a certain purpose. It's very important to understand that. Here I have all kinds of coils. These were radio coils. They are often made cylindrical. This is a medium wave coil, long wave coils. But for other purposes, for instance a choke coil, the whole coil can look completely different. For instance, this coil here, I think this is a choke coil. Also here we see that the windings look like they are braided to prevent the internal capacitance between the windings. And there are many other coils. I don't know where this coil comes from. I think it's from an oscillator. Sorry. Has a ferrite core. Not a typical radio coil. This is also not a typical radio coil. Radio coils look like I showed them, though I have to say that at the moment many radio coils are wound also on shortwave on a toroidal core. So not a cylindrical core, but toroidal. Sorry, difficult. And that has good properties. It can give very sharp peak. Okay, back to these coils. These were the radio coils. And I wish you luck.